Angular momentum or moment of linear momentum. The quantity angular momentum or moment of linear momentum is analogous to linear momentum. What is linear momentum? Consider a point object of mass m and we have applied a force on it. So due to this force, this rest particle will perform a linear motion with a velocity v and it will move a further distance. Due to this motion, it acquires some power and this power we known as linear momentum, and the linear momentum is given by a formula P is equal to m into v, where P is a linear momentum, m is a mass of that particle and v is a velocity. Consider a point object of mass m and it is allowed to move with a fixed distance, say r. Then it is found that the object is performing a circular motion. So when it is performing a circular motion, it is found that its linear velocity is tangential to its path, and due to its mass, it also can have some momentum. So direction of the momentum is also in the direction of this linear velocity and it is also tangential to its path. The relation between this linear momentum and the angular momentum is given by vector L is equal to vector R cross vector P, where L is a angular momentum, P is a linear momentum and R is a position vector from the axis of rotation. So we can say that is the axis of rotation. So object is performing a circular motion with a fixed distance r from the axis of rotation. So it is rotating about this axis passing through this point. So the magnitude of this linear momentum is given by L is equal to P into r sine theta, where theta is a angle between the direction of this r and the direction of this linear momentum. So if the direction of this momentum is little inward side, so the theta value decreases and sine theta value also decreases, hence the linear momentum of the object also decreases, and it is maximum if the direction of this momentum is perpendicular to this uh, position vector r. As the it is perpendicular, theta value is 90 degree and sine theta is maximum at 90 degree, that is 1, and it will rotate with a maximum angular momentum, and its value is 0 when the theta value is 0 or 180 degree, because sine 0 or sine 180 is 0 and the angular momentum becomes 0 as the object will not allow to rotate with a fixed distance. Expression for angular momentum in terms of moment of inertia. Consider a rigid body of mass m is rotating about this axis passing through this point. It is having a angular velocity omega. So this axis is perpendicular to this plane of paper or the plane of this rigid body. Let us consider the object consists of mass m1, m2, m3, m4 and up to the nth particle mm, and they are situated at a perpendicular distance, say r1, r2, r3, r4 and so rn from this axis of rotation. That means the mass particle m1 is situated at a perpendicular distance r1, mass m2 is situated at a perpendicular distance r2 and so on. The nth particle mn is situated at a distance rn from this axis of rotation. As the object rotates, all this particle performs uniform circular motion with the same angular speed omega but with a different linear speed. So this v1 is a linear velocity of the mass particle m1, v2 is a linear velocity of mass particle m2, and so on. Vn is a linear velocity of a mass particle mn. The relation between this linear velocity and angular velocity we can write down as v is equal to r omega. Hence, the linear velocity of mass particle m1 can be written as v1 is equal to r1 omega. Similarly, v2 can be written as r2 omega, and so on. Vn, that is the velocity of a nth particle, can be written as rn omega. We continue the same equation. v1 is equal to r1 omega, v2 is equal to r2 omega, and so on. vn is equal to rn omega. Here we know that v1, v2, v3 are the respective linear velocities of mass m1, m2, m3, and they are tangent to their respective circular tracks or the respective circular path. Let us calculate the linear momentum of the first particle of mass m1 in its magnitude form. Say p1 is equal to m1 v1. Substitute the value of v1 in terms of angular velocity omega. So we can write down the p1 is equal to m1 r1 omega. The direction of this linear momentum of the mass m1, it is along that of the v1. Now, we can calculate the angular momentum in its magnitude as L1 is equal to P1 R1 sine theta. Here, as the direction is tangent to this circular track, the theta we can write down as a 90 degree, and sine 90 is equal to 1, and therefore we can write down the linear momentum of mass m1 as a L1 is equal to P1 R1. Just substitute the value of P1 from this equation, that is m1 R1 omega, and then multiply with R1. So if you do the calculation, you will get the value of L1 is equal to m1 R1 square omega. Thus, angular momentum of first particle in magnitude is given by L1 is equal to P1 into R1, that is equal to m1 R1 omega into R1, and we get the final equation for L1 is equal to m1 R1 square omega. Similarly, we can find out the angular momentum of second particle as L2 is equal to P2 R2. Substitute the value of P1 and we get the final equation as m2 R2 square omega. L3, that is the angular momentum of third particle, is equal to P3 R3, and that is given by m3 R3 square omega. Similarly, we can calculate the angular momentum of nth particle, that is Ln, is equal to Pn Rn, and that is equal to Mn Rn square omega. Now, for a rigid body with a fixed axis of rotation, all these angular momenta, that is a L1, L2, L3, and so on, the Ln, are directed along the axis of rotation, and this direction can be obtained using the right hand thumb rule. In this case, if the curled fingers are in the direction of the rotation, then thumb denotes the direction of angular momentum. As all of them have the same direction, their magnitudes can be added algebraically. To calculate the expression of angular momentum in terms of moment of inertia, we have to add all the magnitude of angular momentum of this body. So we can write down the equation as L is equal to L1 plus L2 plus L3 plus dash 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 plus Ln. Just substitute the value of L1, L2, L3, and we get the equation as L is equal to m1 R1 square omega plus m2 R2 square omega plus m3 R3 square omega plus dash 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 plus mn Rn square omega. Now we'll take the common factor omega out of the bracket, and we can write down the value for the angular momentum of a rigid body is equal to bracket में m1 r1 square plus m2 r2 square plus m3 r3 square plus dash 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 plus mn rn square and multiply with this common factor omega. Now we know that the summation of the product of mass and the square of the perpendicular distance is nothing but the inertia of this rigid body, and hence we can write down the I is equal to summation of mi ri square, where I stands from 1 to n in this equation, and we get the value of linear momentum of the rigid body is equal to I omega. So this is the expression of the angular momentum in terms of moment of inertia. So this expression of angular momentum L is equal to I omega is analogous to the expression P is equal to mv of a linear momentum if the moment of inertia I is replaced by the mass factor m, and which is its physical significance.